In this video, we'll obtain the channel capacity for a Gaussian channel. And in a Gaussian channel, the relationship between the input and the output is as follows. At the output, what we have is the input plus a noise term. Z is a Gaussian random variable with zero mean and a given variance. And the variance is equal to the power of this noise in this case. And we are going to obtain the channel capacity under the following conditions. With a constraint in the transmitted power, the power of X is limited to Px watts, and taking into account that usually the transmitted signal is band limited and the bandwidth in hertz is B. This means that at the receiver we'll have a filter to limit the noise power. If we consider an ideal filter, the noise power after this filter is N0 times the bandwidth in hertz. With these constraints, it is possible to obtain the channel capacity just by using the definition related with the mutual information. The channel capacity is given by the mutual information between the input and the output of the channel, with the maximization made in the input distribution, and here we include the constraint of the power in the transmitted signal. It is possible to obtain this capacity. In many books you can find the analytical deployment to obtain this capacity. And this is the capacity. The bandwidth in hertz times the logarithm in base 2 of 1 plus the ratio between the power of the signal and the noise power in bits per second. This is a very well-known result that can be obtained through the channel capacity. Now we are not going to obtain this result in this way because it is available in many bibliographic sources, and we are going to see that it is possible to arrive to the same result in a more intuitive way. And in this case, starting from the same problem statement, we have a limitation in the transmitted power. If now we plot the m consecutive samples of the signal that we transmit in a n-dimensional plot, as a vector of dimension n, the power limitation becomes a limitation in the radius of the hypersphere where these vectors are contained. This radius is a square root of n times the transmitted power. Now, during the transmission, noise will be added to every set of n samples of the signal, and the noise will be around the corresponding representation of the signal, and the noise power limits the separation with respect to x to an hypersphere whose radius is given by the noise power, is the square root of n times the noise power. Finally, taking into account that the signal and the noise are independent, the power is additive, and the representation of the signal plus the noise is contained in an hypersphere, the green one in this picture, whose radius is given by the addition of the power of the signal and the noise power. In fact, it's the square root of n times this addition. Taking this into account, now the channel capacity can be stated as the problem of analyzing how many hyperspheres of the radius given by the noise can be placed with non-overlapping in the hypersphere defined by the addition of the signal power and the noise power, the green hypersphere here. This is a very simple trigonometric system. This is the number of non-overlapping spheres in the green hypersphere. Then the channel capacity is the logarithm in base 2 of this number of non-overlapping spheres. This is the number of bits that we can transmit divided by the number of uses of the channel, the number of samples. it's straightforward to obtain this expression if we replace here the expression for the number of non-overlapping spheres. And this is the channel capacity in bits per use. Now, if we take into account that for a signal of bandwidth B, the number of samples, the number of transmission per second, will be 2 times this bandwidth according to the Nyquist sampling rate. Now 2 times B times 1/2 becomes B, and we obtain the final expression for the channel capacity. The bandwidth in hertz times the logarithm in base 2 of 1 plus the ratio between the signal power and the noise power, N0 times B. If we analyze this expression, in this expression we have two parameters, the signal power and the bandwidth. If we consider the dependence with respect to the signal power, we can see that the signal power is here. There is a power inside of the logarithm. The logarithm is a monotonic increasing function, and this means that it is possible to increase arbitrarily the channel capacity by increasing the signal power. However, it must be taken into account that the signal power is inside of a logarithm, and therefore, to obtain a linear increase in the channel capacity, it's necessary to have an exponential increase in the signal power. But theoretically, it is possible to increase arbitrarily the channel capacity by increasing the signal power. If now we analyze the bandwidth, we have two terms here, and this term will tend to increase the channel capacity if we increase the bandwidth, but we have also here the bandwidth in the denominator of this term inside of the logarithm. Therefore, this term will tend to decrease the channel capacity if B is increased, and there is a trade-off. It is possible to compute the limit when the bandwidth goes to infinity, and this limit is finite. This is the ratio between the signal power and N0 times the logarithm of the Euler number, 1.44. And this means that, unlike with the signal power, the increment of the bandwidth of the system doesn't allow an arbitrary increment of the channel capacity. We can increase arbitrarily the channel capacity by increasing the power, with the remark that only a linear increase is obtained with an exponential increase of the power, taking into account that we have here the power inside of the logarithm, but with the bandwidth, to increase the bandwidth will not increase the channel capacity arbitrarily.